So we were on the audio compression last time. Let me finish this. Now we can come back to it. And the audio compression standards are called by the G number. G is actually the committee in ITU. ITU has committee A, I mean actually they may not call committee, they may call it groups or something, A through X. So G does this audio compression and their standards are called G.711, 729 and all that. You may forget all the G numbers, but G.711 you have to remember all the time. 711 is the uncompressed 64 kilobit data, 64 kilobit voice. And the reason it became 64 kilobit is because AT&T, the first telephone company, did a survey and found out that people like 8 kilohertz voice, 4 kilohertz voice. They have to sample it at 8 kilohertz, and each, if it is sampled at 8 bits, is good enough for common conversation. It's not good enough for video. It is not good enough for music. So it was not designed for music transmission over the wireless or wired phone either, right? So that is how 64 kilobit comes forward. G.711. That number you should remember, please. Okay. Any question about that? Was your question related to this or something else? Okay, all right. So then we come back to video compression. Video compression also nowadays it is so common, everybody knows that there are MPEG-4, MPEG-1, MPEG-2, MPEG-3 and all that. MPEG stands for Motion Picture Expert Group. Again, there is an ITU group which works on video. All right, and actually it's not just ITU, it is combined with another organization, so this is actually somewhat separate, and so therefore they don't use just A, B, C, D, H numbers. They have their names with MPEG 1, 2, 3, 4, 5, 6, 7, so on. I think they're up to MPEG 7 by now. So MPEG 1 was the initial standard, the simplest standard, which produced CD quality video at 1.5 megabits. MPEG 2 was a better quality DVD quality video at 3 megabits, and MPEG 4 is actually lower rate but high quality. So that's the interesting part with MPEG 4. The quality is good, but the rate is low. You get so if you see the extension like MP4 or DIVX, that means that the rate may not be very high, the files may not be very big, but they are good quality. Okay, and then there is a standard called H.261. By the letter H, you can see that is a pure ITU standard, and what that standard is actually is going to come up later on is more of a set of things that you have to do to get video quality. All right, so these are all the video standards. Now when you want to transmit video over the wireless or wired network, nowadays we do so much wireless video that wired video is almost like we don't even think about, but wireless so much is that you could have a streaming video. A streaming video means something that is being sent to you as it is being basically, well, streaming video, most of the video today is streaming. There are two ways. You could just get the video file and then play it locally. That is not streaming. On the other hand, you could get it while watching it. That is streaming. Now, while watching it, the video could be real time, in which case you are talking to somebody and you're looking at their face. As they move their face, you see it moving. That is live streaming. But much of the video is not live streaming, it is stored streaming. The movie is stored there and you are watching it. In that case, for stored streaming, you need a totally new different set of protocols. Because in the stored streaming, you might want to rewind. In the live video, you cannot rewind it. But in the stored video, you might want to rewind and fast forward and so on and so forth, right? Just like you do on a tape. So we need a streaming protocol. And you might need a streaming server. So they have two kinds of server, a web server, which is a normal HTTP server, or a streaming server, which was initially designed by Real Media. And now basically everybody has it. So basically streaming server. So your request, when you get a page which says, okay, I want to watch a video, and it might be a YouTube video or whatever, is that the page has most of it is HTTP. Inside that there is some media, a special media. That window might be getting the data from a streaming server. Okay, so YouTube might have a special server which can allow you to do everything that you want to do, rewinding, forward, baiting and all that, streaming media. So you might have different server, although sometimes people have just one server and then you really don't get streaming with this. If you just have a web server, then what you get is the whole file. If suppose you go to my website, you can't really stream on my website because CSE does not have a streaming server. You just have to download the whole thing and watch it, right? So that's the thing. All right. So the real-time streaming protocol is designed for streaming, and this is the one that allows you to start, stop, pause, fast forward, and rewind a stream. And so it has two channels, a data channel and a control channel. Why data channel, control channel? Data channel is what you are watching, control channel is what you are pressing the button on your remote control, right? If you are saying reverse, that is a control command. And so those go on a control channel, and when the movie comes in, that comes on the data channel. All commands are sent on the control channel, which is port 544, and the protocol is specified like this. You can say RTSP, which is the real-time streaming protocol, colon, slash, slash. That is the name of the media. Okay? RM is the real media file, yeah.
Could you go back a slide? Could you explain the middle arrow from the web server to the media?
Yeah. You could get the media from the web server, like I said, but in that case, you really will not get all the facilities that you get with the streaming server. You can go back and forth. You'll get the whole file.
Can't the media player just ask for a piece of a file and then another piece ask for a chunk of a file?
So the thing is, this is what this is designed for. Streaming server is designed to give you basically piece by piece as you need. And this one is not designed for that, although having said all this, everything is being mixed up nowadays. So you could have a web server which understands streaming, and you could have a browser which understands streaming. So this is how basically the functionality was different, or it was designed to be different. Web server is simple HTTP command. You say get and it gives the response, period, done. But a streaming server, you can say stop, rewind, forward. All right, now whether your server can do this, it's quite possible they can. All right, so here are the commands for RTSP. To the web server, all you can say is get. To here, you can say set up, play, pause, stop, tear down. So all the commands, all the buttons that are on a remote control at home for DVR can be sent over a network. RTSP allows you to do that over a network. Basically, it has commands, just like your button. Yeah.
So if I click pause on like a YouTube video, then the server knows that pause even though it keeps loading.
Okay. I don't know whether they use RTSP.
Oh, okay.
Okay, but they might have their own. See, nowadays with Java, anybody can write both sides of the story, right? So they have their own player here, they have their own server there, and they could have their own protocol, right? But RTSP as a standard, when it says pause, it will, if nothing else, the client will pause. Now, whether the server is keep sending, whether the pause is sent to the server, could depend upon the client's smartness. Client could say, well, I should still keep 3 seconds ahead anyway, just in case you come back, right? But strictly speaking, client could pause, and then you could say, well, move forward 1 day or move forward 1 hour, and it should just send that command to the server saying that move forward 1 hour. Right? So the commands are all there. How they are used in YouTube, I don't know.
YouTube isn't using Java, so it has to be using some sort of protocol.
Huh? YouTube is using?
Isn't using Java, so it has to be using the public protocol.
Use Flash,
Okay, so I don't know about YouTube, sorry. So yeah. But the thing is, here thing though, if you use Real Media, which I use, Real Media is all my website, you go and you see Real Media. So RTSP is there. Before this university, I had the streaming server, we had RTSP URL all over my website. But since I came here, there is no RTSP server, so I don't have any RTSP command. So, but you can use RTSP today. I mean, in many website providers provide streaming server, and if you put your website there, then you can incorporate URLs like this in your web page. All right. If you incorporate URLs like that in your web page, then you can do all that forward. Yeah. Question here.
So, for live streaming, is there any buffering going on as well?
For live streaming, buffering is not possible. I mean, like in the sense that the more buffering you do, the more unlive it will be. So suppose you are talking on the phone to your mom, and then suddenly she says, "I'm coming," and then you hear after 1 second, that doesn't look good at all. I mean, so thing is, it has to be immediate. Yeah.
There's no control channel in live streaming, or?
Oh, there is a control channel. Basically, the thing is, control channel has a different purpose. It's like even in the HTTP, the channels are mixed up, but this is a control command. Get is a control, right? And this is not, but the data is here. So similarly, in the live streaming, there is a session setup. When you do what you call FaceTime, when you do FaceTime, that is live streaming. You know, so it takes few seconds to get it connected and to both sides to get ready. But after that, basically you disconnect. So there is control channel. Yeah.
What does the teardown mean?
Tear down is close. All right, so all these commands are there in that protocol. And so here is the sample protocol. So you might send a command, and this is basically they selected just like HTTP, an ASCII protocol. So you can read the messages. The message might be set up RTSP : RTSP/1.0. So this is saying that set up this media using this protocol. Transport, I want to use RTP and UDP with compression port number 3056 and play. Then this is the client says. Server says, okay, 1.0 is okay, and my session is 4231. Then it says, client says, play that other media and range, start from beginning. All right, it could have said range, start from 1 hour. Then it says pause and session and range. So it pauses the session, that one, right? And then tear down, the connection is tear down. So these are basically examples of the commands, how they are sent. They are basically English commands. Okay? All right, so that is all about RTSP, real-time streaming protocol. Yeah.
I have a question about the, go back to slides. This one, the command set up play, pause, tear down, these are examples of commands that are run through the data channel, right? And
No, hold on. Commands do not go through the data. Commands go through control.
Oh, so that's the data,
This is the data channel right here. The blue one is the data channel.
and the rest is the control?
Yeah, most of it is control. Yeah.
Question about slide 7-5.
7-5. Why?
Yeah, two questions. Why full field noise is 8,000 samples and not 4,000 samples?
Oh, okay. So this is Nyquist theorem, is that when you want to create a waveform which is 1 hertz, you have to really sample it twice in one cycle. So the sampling rate is always twice the rate of the signal.
Okay, and the third bullet, what is that? PCM?
PCM is the pulse code modulation. That basically means that you just get the value. There are many ways to so basically you read the value here. If you are sampling, you know, I mean actually I made a very nice signal, but let me make a signal. Your sound might be like this. Okay? Then you sample it. Right? And you read this value, and you put that into binary, that is called PCM. Okay. Okay, we are done with that. So now let us see what do we do for putting multimedia on IP. IP simply provides best effort service. And so there are three things that, one thing that can be done is that we can basically compress it. That way we have very low rate. If you wanted 10 megabit video, very likely that most of it will be lost on the way. But if you want 10 kilobit video, very likely that it will make it through the internet. So most of the video today is very low rate. It was not used to be that low rate before. So as you noticed, MPEG 1 through 4, MPEG 1 was 1.5 megabits. You couldn't do much video on the net. MPEG 4 is in kilobits. So we are all watching video now because it is in kilobits. And the reason it has become better is because of the compression. Now we have better compression techniques that makes it low rate and low loss. Now 1 to 20% loss can be concealed. So if you lose 1 to 20% of the packets, people will not notice it. And they will notice it, but they will live with it. Eyes are more forgiving than ears. If you lose 20% of the video, the eyes will forgive you. If you lose 20% of the audio, somebody will disconnect on you. So when we do audio video, we want to make sure that the audio gets better quality of service. Audio goes there first, and the video gets lower priority. Everybody understand that? All right. Forward error correction is used. So we might put some extra bits before sending. So if we lose one packet, we can reconstruct that packet. Instead of 2 packets, we might send 3 packets. Forward error correction. End-to-end delay is limited to 400 milliseconds. Now for audio at least, if the delay is very large, then people don't like the sound. And we already mentioned this number before, 400 milliseconds is the kind of limit. And the jitter is overcome by playout buffer. I think this is a repeat of something they already said. So jitter is the variability in the delay. And that's why we keep the buffer at the end, so that even though the packets are coming irregularly, but we are playing them regularly. And if the jitter becomes very large, then the buffer, we will not be able to get the packets on time or play them on time, and they will be no good, and therefore we will have to lose them. Each chunk that comes, the chunk of voice that comes or a video that comes, has a sequence number and time stamp, so we know when to play it. And playout delay can be adaptively adjusted according to the major delay variation. So basically what we do is, when we start a new connection, we see what is the variability for the first 5-10 packets, and then accordingly we set up that we will not start the first packet until we get 10 seconds of video or 2 seconds of video or 1 minute of video. That is determined by how much variability is seen. So here is what the video should look like. Basically you would like to have constant bit rate. You want to have a packet every 30 milliseconds. Actually we watch, most of the video we watch, or most of the video we want to watch, is 30 frames per second. 30 frames per second is 33 milliseconds per frame, right? So that's what we want to see. So every 33 milliseconds we want to see a frame come in. Obviously it doesn't come that way. So what we do is, the packet is coming like this, so first of all we have to wait this much anyway, but we wait even longer before we start playing. So what we do is we delay it and then we start playing. At this point we should have all the packets that we need. So they should have arrived, packet number 1, 2, 3, 4, 5, they should have all arrived before they are needed to be played. If these curves ever cross, then the packets that came late cannot be played. Yeah.
What's the usual time delay between the time it's sent and the time it's played at the other end?
Oh, this is no, there is no particular, number can be given, but you can watch it on YouTube. If I make it 2 or 3 minutes, I don't think you're going to watch that TV. So there is a human tolerance. And at the same time, the networks are mostly in seconds. So the network's delays are in seconds. And So the human tolerances are in seconds to minutes. All right. So you need to determine the playout delay. So basically what you do is when you get the packet, you don't play. For the first few packets, you see how much is the variability, and then you allow for that variability by putting a buffer. All right, so there is a little mathematics here. You need to read in the book, and this will be in the exam again, and the exam is next Wednesday. Okay, so I just want you to carefully listen to this. This is mathematics here. It may not be clear here, but basically for each packet you calculate the delay. The delay of the ith packet is the delay of the previous estimate of the delay, 1 minus a times previous estimate of the delay plus the estimate of this packet. So basically this is exponential weighted average. Ri is the receiving time, Ti is the sending time, so this is the delay. Ri minus Ti is the delay measured, this is sample delay, and you keep an average. Similarly, you keep a variation, and then you start that I will wait for so much of the average plus so much of the variation, let's say 4 times the variation plus the average, and then I will play. Alright, now this 4 times is not fixed. You could decide 5 times, you could decide 6 times, but basically what you are trying to do is by saying 4 times, you want to really make sure that you get 99%, 99.9% or some percentage of the packets in that window, time window. So that is basically, and actually I'm going to go through one example I think later on. No, we are not going to go through example. But so basically this thing you can plot as shown here, and then once the playout buffer is decided, then you can calculate how much delay is left. If the delay becomes negative, then basically a packet arrives late, and that's what you need to be careful about. All right. Next thing is, how do you recover from the packet loss? So we said you can do 2 things. First is you can do a forward error correction. That means that you send more bits than you need to send. You can send n plus 1 packets instead of n packets. So you can send 4 packets instead of 3. And also you can do is you can make the packets such that if you lose a packet, you don't lose a whole scene, you lose some part of a scene. So for example, this first packet contains 1, 5, 9 and 13, and the second packet contains 2, 3, 4. So if you just lose this whole packet, you would have lost 3, 7, 11 and 15, and you can still play 1, 2 and 4, 5, 6 and 8, and these little delays are much more bearable to human beings than if you had to have that big delay, big loss. Yeah.
How do you send small packets? Duplicate packets in advance?
No, what you do is just like a parity bit. See, the parity bit is 8 bit plus 1 bit, right? So you could calculate a parity packet. You have 4 packets, you just put them vertically and then calculate the parity for bit by bit. So now you have a 5th packet, which is simply a parity packet. As long as you get 4 out of 5 packets, you can construct it back. Just see what I mean? So you send, so there are whole error correcting codes people use so that you get extra packets, extra bits. So instead of putting the extra bits into the same packet, you put extra bits into extra packets. Excuse me, over there. Please pay attention to the class, turn off your computer. All right, so, yeah.
On real-time applications like voice over IP and Skype, how do you mitigate the delay in the network?
How do you make up the delay in a network? Yeah, so for the voice and Skype it is difficult, and that's where the Skype's innovativeness lied, that they made it possible that basically with proper coding and proper error corrections and everything else, the voice is acceptable in spite of all this variation. Now, so one technique that is used very commonly is error, is that if you miss something, you just replay the previous one. So if you miss 11, you can just play back 10 2 times. All right, and that works in many situations. If you listen to my lectures on the recording, sometimes packets are lost, and you might hear me saying da 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 da. I just said only once, but the computer played out 4 times because they lost 4 packets. You see what I mean? So that is a common error concealing technique. That is called error concealment. Is that you hide the error from the user. I mean, and similarly, when you see a video on the screen, sometimes you see blocks, right? That is because they lost some packets. Yeah.
I understand the video, why that would be helpful, but in audio, why wouldn't they just...
No, the thing is, here thing. If they played a 0, you would disconnect. So 0 is bad because people don't like a deadline. So noise is better than 0. Right? And the same person's voice second time is better than noise. Right? I mean, if suppose somebody puts you on hold, what do? They do 2 things. Either they will have some noise going on so that you know that it is alive, or they will put some music. Right? If they just put you on hold, you don't know whether they are there or not, right? So that's the thing. Okay. All right. So we saw lots of techniques here. We saw interleaving. This is called interleaving. We saw playing out the old syllable. That is called concealment. We saw that the low resolution stream. No, we didn't discuss this one. But you send a low resolution stream in addition to the correct stream. So you are watching a 10 megabit per second video page from what is the name of the company that supplies movies? Netflix. So you are watching Netflix. They might send a 10 kilobit video also, just in case that 10 megabit doesn't make it. They can play, instead of a noise, they can play a low resolution screen. So that's another error concealment. And then obviously this is error correction, forward error correction. Another thing that is happening is that basically people figured out that the video and audio require very low delay because nobody wants to basically have long round trips and jitters. So they put the servers everywhere in the world. So for example, Akamai is a company that has put hundreds of servers throughout the world. And you can put your audio video with Akamai. If you are a company, you can basically get the service of Akamai. They will put your videos on their servers. And when somebody in China wants to see your video, they will serve it from China, not from USA. Understood? All right? So the local copy is served. So that way everybody gets fast service. So that is called Content Distribution Network, CDN.
There's a lot of duplicated data, though.
It's a lot of duplicated data.
Doesn't matter, though.
And it has to be a lot of static data too, because if you are changing every second, Akamai cannot handle it. But they can handle Netflix very well. Right? All right. So now the IETF or the IP people also thought about what to do for the real time, and they designed a transport protocol called Real Time Transport Protocol. Actually, the name is a misnomer because TCP is the transport protocol and UDP is a transport protocol. RTP runs on the top of them. All right, they should be calling it session protocol, but it is called transport protocol. And so what it is that it adds some more fields on the top of these RTP. So on the top of UDP, it adds some more fields that allow all the real-time applications to use them. Basically, every real-time application had their own way of somehow indicating the time, indicating coding, and so on and so forth. They said, no, hold on, let's do a standard protocol so that all the applications can use some standard method of talking to the other side. So that is RTP. RTP is the real-time component of the transport protocol, if you want to call it that way, but it runs on UDP. So here is what it has. It has a payload type. So payload type, for example, could be a 64 kilobit voice, a 13 kilobit voice, 2.4 kilobit voice, could be a motion JPEG video, could be H.261 video, could be MPEG-2 video. So these are all the things that you can. So basically, once you say this, use RTP, you put the payload type, the other side will know what you're using. These numbers are all standard. Then there is a sequence number, which is simply the packet number. Then there is a timestamp, again standard timestamp, GMT timestamp. Then you have synchronizing source identifier. So this is basically the stream number. So basically, you might have many things going on in parallel. In particular, you might have a stream, audio stream, you might have video stream, you might have a screen, you might have a data stream, right, in that session. So all those things are put here, and miscellaneous field, and there are other fields. Okay, yeah, go ahead.
Why do you need the timestamp?
If you don't have a timestamp, how would you know what time this packet has to be played? No, sequence number, okay. Sequence number is good if all the packets are exactly timed, then maybe you can convert the time into the sequence number. The packets could be, say for example, your screen. Your screen doesn't come in every 30 milliseconds. Your screen comes whenever you press a key.
So it's like, it's not the time?
So time is different than sequence number. That you should understand, right?
Yeah, that's different. I'm just like wondering.
Yeah, so time is required for presentation. Time is basically the time of generation, and that has to match with the time of presentation. Sequence number is simply I made 2 packets out of 1, or I made 15 packets out of 1. Sequence number could be anything. That doesn't indicate time.
So not all the same.
Yeah.
Packets are the same size?
Yeah, no, not all the packets could be same size. It could be different sizes and the different rates, because different rates. So I mean, they could be. So you cannot just make out the sequence number. So you need a timestamp anyway. Just all right. All right. So in addition to RTP, now they did. This is IP days, right? So in IP they have IP protocol, which is a forwarding protocol, and then they have ICMP, the control protocol. So RTP has a control protocol which goes with RTP called RTCP, real-time control protocol, or RTP control protocol. So RTP control protocol is something which does not carry data, but it carries control. Control is anything that is required to make that work. And so let's see what it does. RTCP is a protocol that is run along with the RTP, and using this, the receiver sends a report to the sender. So the receivers, movie is being broadcast to 15 people here, 60 people here. 60 people will send the report back to the sender saying that I am missing every 10th packet. I am missing your 90% of your packet, something like that, right? And then the sender can do something about it. So this feedback is done using RTCP. So also used by sender to report stream information. Another thing RTCP can do is broadcast something which is not really data, but say, well, I am going to broadcast my lecture using MPEG-4. All right. So RTCP can be used for that. It can be used to adjust the transmission speed, quality, or for diagnosis. And it can be, basically it contains SSRC, which is that synchronizing source number. So basically you know what stream they are talking about. Fractional packet last sequence number received, inter-arrival jitter. So these are the kinds of things that you can send it back. Receiver report rate is adjusted inversely number of the receivers. So that's another feature of RTCP. And it's the important feature is that if there is one user, one receiver, then the feedback will come very fast. If there are 2 receivers, then the feedback will come at half the rate, so that the total feedback is same rate. So let's say I can take 10 packets per second. If there is only one user, I will get 1 packet, so 10 packets from one user. On the other hand, if there are 2 users, they will send me 5 packets per second each. So the feedback is still 10. If there are 3, I will get 3 from each of them, or 10 divided by 3 from each of them, and I will get 10 total. So the receiver report rate is adjusted inversely to the number of receivers. and the sender report rate is adjusted inversely to the number of senders. Now there could be multiple senders too. For example, in a group conferencing. In a group conferencing, n people are talking to n people, right? So there are n receivers and n senders. So that's also adjusted. Total RTCP traffic has to be less than 5% of the media data rate. So this is a guideline that basically you don't want to have the network consumed by these reports. So keep it below 5%. All right, so that is the second protocol. So we already talked about three protocols so far. If you remember, RTSP is for what? Streaming. RTP is for what? To indicate what is in the packet, right? To indicate the type and all that, sequence number and so on. RTCP is for feedback of RTP as to how it is going. Now we have the fourth protocol called SIP, which is actually probably the most important protocol and the latest of the protocols. SIP is only 10 years old, whereas RTCP and RTSP are 20-30 years old. So SIP is the session initiation protocol, and this was designed especially for voice and video conferencing over the internet. So this was designed when VoIP started becoming popular, then people needed a standard method of initializing a session. So it's called session initialization protocol or session initiation protocol. It allows you to create, modify or terminate session with the participants, and it carries session description for user negotiation and user location, call setup and call transfer. So this is what you can do with SIP. And many of you are using SIP on your iPhone or Android phone. Basically, what SIP allows you to do is to set up a session. So I want to talk to you. I send a SIP message to your phone or your computer. Skype actually doesn't use SIP, but everything like Skype uses SIP, by the way. But Skype doesn't use SIP. But so I send a SIP message, and SIP message could be that I want to talk to Jane at CSE. And then it might say, well, Jan at CSE is right now at Jan at home. So then the message will be forwarded to Jan at home, and it will ring over there. So locating the user is one of the things that SIP can do. And I could program my SIP server to say, well, Jan is not available at home, and play this, something else. So the call can be redirected. So user location, call setup, call transfer, all of this is supported by SIP. And it allows proxying and redirection. Proxying means that you could have somebody else answer your phones, right? Redirection is that you could move your calls to some other place. So all of that is possible with SIP. Now SIP also uses, very similar to HTTP, they have a URL which is like SIP : this is a URL possible. This is another URL. Okay, here there is a phone number and the organization and then the subject field. So this is very similar to the mail to URL. What is this? Is a port number? Yeah, that's a port number. So I'm listening on that port. Yeah. No. So here you think this is all made up. But this is not a real AT&T phone line. This is a phone line which happens to go to osu.edu. Over there, there is a SIP server which is listening on port 123, and then somehow knows what to do with this number here. It looks like a telephone number, but it's just a number for the SIP server, right? And on my phone, it might even say that you are 614-292-3989, because that's how people understand everything, right? But this is all SIP command. All right, SIP can use UCP or TCP. SIP messages are sent to the SIP server, and so you can register. Basically, so there is SIP registrar. You can register and say, well, here I am, and then there is a directory which can figure out where you are. You can redirect, and you can have proxy and all that. So now let me just say, how many people have used? Actually, so there are some SIP programs available for the iPhone and for Android. Has anybody used that? Okay, so you know basically SIP, you have used this, basically that's what this is. That protocol allows you, and you generally when you use those programs, first just like Skype you log in, so that is your SIP server who knows that where you are, right, and that you are alive right now, or you are not alive, you are online right now, all right, and then if you are logged in on a computer, then it knows you are logged in on a computer. If you are logged in on a phone, then it knows you are logged in on the phone. If you are logged in on something else, and there are many things you can log in on. I mean, we have nowadays SIP phones. And so it will remember that, and when a call comes to that particular thing, you know, it forwards that. All right? So SIP is for VoIP, and since it is for VoIP, it can be used for video as well. So if you are going to do video conferencing, it's exactly the same thing. Right, FaceTime, and I would not be surprised if FaceTime is just SIP, although I don't know. But I know that the Skype doesn't use SIP. So because of that, most of the SIP programs cannot talk to Skype. All right, but there are lots of other companies which offer SIP-based services, and they can talk to each other. Okay. All right, that's all we are going to say about SIP. Here's an example that there is a command called invite in SIP. So somebody could say, I want to invite Jan at CIS or CSE, and it could go to my redirect server, and it will say, no, Jan has moved to Jan at ACM. It could go to Jan at ACM, and so basically, you know, you can register with the server, and you can tell them where to send your phone calls to, and then there are messages like act, buy, invite, register, redirect, so on and so forth. Here is a message sequence. SIP invite, it goes to the computer, it goes to the server actually, this is not a computer, this server, and then it sends the invite to the other side. So you are trying, this A is trying to reach B, so this, it says SIP invite to B, this is sent here. On this side it says SIP trying, and then this phone will start ringing, so it will say, okay, I am ringing right now, and then that message will be sent here, so your phone will hear a ring, I'm coming. So your phone will hear a ring. Once this picks up, somebody picks up the phone, then it will say okay, that okay will be sent here, then you will say okay, I'm okay, all right, then you can start talking. Once it is talking, then this will say, I want to put down the phone. They put down the phone, it says SIP by. Then here you get a SIP by, and then it says, okay, so it's done. All right, question?
On the previous slide,
Yeah.
the initial message, why does it go to the redirect server instead of...
Oh, basically it goes to Jan at CIS, that's it, period. So it goes to the server, whichever server is for CIS, and there it basically, the server says, you know, he is not here.
So they're basically the
Same thing, yeah. It goes to SIP server. And here everybody is clear with this one? What's happening? Yeah.
The SIP, it works on TCP or UDP?
Okay, so it works on both, it said, right? It said that it works on both TCP and UDP. Okay? It can use TCP or UDP. All right. Moving on to H.323. So this is what we would call a VoIP protocol set. Actually, this is not a protocol, it is a protocols. And so what this is a whole set, and this allows you to do voice and video over the local area networks. And what it is basically, if you read this standard, it's very boring because all it is a list. So it says for video you can use H.261 or 263. For audio you can use, you know, blah 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 these numbers. For control you should use RTCP, and you can use H2. You know, these are other alternatives. 45, 225, 000, so on and so forth. So anyway, so the idea is if you have a H.323 device and the other side is H.323 device, then you can negotiate with them some common protocols for each of these things, for audio, for video, for control, and for data. Hold on. And so it is so for each of these possibilities, for example, audio, they might be implementing just some subset of it. So there is some required subset. Everybody has to implement 711, for example, right? So that way you can find a common subset, but generally you will try to negotiate something better like 729, which or 723.1, which has a lower rate, same quality. So but all this is a protocol set which allows two sides to negotiate the appropriate option that both sides implement. So all it says is here's a set of protocols we allow, and then you implement some subset, and there is some required subset which is their default subset. Yeah, go ahead, question now.
So TIVA 123 you can use without IP or TCP or UDP.
Which you can use what?
TIVA 123 from data.
Yeah, this you can use without.
Yeah, so if it's not using IP, then how does it go from router to router?
Oh yeah, so the thing is, there are networks. The thing is, now there are not that many networks, but there are networks that don't use IP. They used to be in the phone world. But nowadays everything goes over TCP and IP.
So is that?
So that is, maybe that is, it could be like fax. I don't know what number is fax. Fax has some T number. I forget the number for fax. But fax doesn't go over IP. Right? So similarly, these protocols are not designed for IP. These are old telephony protocols. For example, I'm making it up here, is that if we were doing a over a telephone line, a video conferencing, we could use that T protocol to send the data, whatever it is, right? But there's no IP involved at all. But nowadays everything goes over IP, so we are more on this side here. So that brings to the end of this module. And so the 5 key messages are that the multimedia applications require delay, bounded jitter, and minimum throughput. And the way we are getting better multimedia today is for 2 reasons. First of all, the media has become better. The multimedia has become better. They just compress. Previously, we did not know how to compress so well, but now we can compress to very low rate, but still have the good quality. So we haven't heard about MPEG 7. MPEG 7 is even very low rate. Okay, so that is what is happening. Second thing is networks are becoming faster, so that helps. So service guarantees, we did not talk about this one, but basically RTSP allows streaming controls like pause, forward, and so on and so forth. And RTP allows sequencing and time stamping, and then it goes with RTCP, which is control for RTP, and then the SIP allows the session negotiation or the parameter negotiation. Okay, that's the end of this. Any question about this chapter? There is no homework. Homework is there, but let me just talk about this first of all. So the next Wednesday is exam. So I don't want to give you homework today, but you should do all these problems that are here on your own, and you should do this homework on your own. Yeah.
Us the answers on Monday.
If you do it by bench day, I will show you the answer on bench day. Yeah, just do it today, because Monday there is no class.
Can you show the answer right now?
It doesn't help. I really want you to do it first. Every time I said solution without knowing it, what will happen is that people will say, can you put it on the net because I haven't done it? Well, please do it. And then you will not need to put it on the net, because then you can just check your answer with my answer. So please do it on your own. If you don't have to do it, then you don't have to do it. But basically next Wednesday is the exam, and you might as well do it.
Also, one time is really easy.
Eh? Okay, go ahead.
Did you say there's no class on Monday?
There is no class on Monday. So this Wednesday is the last class. All right, so this is the homework, right? Now homework is homework is simple. This is the arrival, this is the reception, and obviously they're not arriving the way we want them, but suppose we select the delay a particular value and then we start playing, then some packets will be late. Which packets are late? Just calculate the delay and then packets are late. So please do it on your own and then I will show you the answer.